So welcome back. This is basically the continuation of data types. So this is going to be episode 6. This is going to be part 2 of data types in MPI. We covered up until create h-index. We saw the example. Now we're going to move on to the next one, which is index block. As you might have guessed, index block is quite similar to MPI type index, but the only difference is that the block length is now the same size for all of the blocks. So let's take a look at indexed block. So here we're gonna skip these. We don't care about them, but what we do care is this sort of call here, which is create index block. We give count. This time we don't have any array for block length, so we don't have any different arrays because it's a block type. So it's gonna have a single number, sort of a single integer block length. That's the only difference. The rest of the stuff is the same. The displacement array works with not the number of bytes, but it works with the number of elements of the old type. That's the difference between the starting and the last point. So this is, again, exactly the similar strategy is followed. So that's why I said that these examples are super nice and in harmony with the text. So let's compile this. Let's run it. So this is exactly the same. Size of the buffer is 96 because we had 6 elements, or 6 times the extent of 16. That's what we said. Okay, the next one in the list after h-index is after index is h-index block. It is also very similar to h-index, but the only difference again is that the block is not an array, but it's just a single number. So let me clear the space here. Vim h-index block. Again, skip these stuff. What we care about is here, MPI type create h-index block. And the only difference is this one, that you pass in a 3 here. And just like similar to h-index, which gets displacements as in bytes, h-index block, its cousin, it's also using sort of number of bytes. So we had 3 elements difference, if you remember. So 3 times 16 is going to be 48. That's the only difference. And the rest of this stuff is literally the same as previous examples. So MPI CC h-index block and MPI run, and you see that everything works perfectly. Next one in the list is the struct. Okay, this is the most beautiful one. And now you're going to see how we created that double 0 character 8, that pattern. Because MPI type create struct is the most general type constructor that we have. It further generalizes the MPI type create h-index in that it allows each block to consist of replications of different data types. So see the example struct.c, we're going to see it in a second, but take a look at this. This gives you a lot of flexibility. It gives you an array of different block lengths. It gives you also an array of different displacements between each start of the block. And then it gives you the flexibility to have also an array of different types. So that is why, if you take a look at here, this is the pattern that we talked about with double at 0, character at 8. So our block length has an array. The length of it is 1 and 1. We're going to have 1 double. We're going to have 1 character. Our displacements is going to be 0 for the double and 8 for the character. And then the types, it's an MPI data type. This one is also a sort of array, and it contains so this is a heterogeneous data type. That's what I was talking about, heterogeneous. Why? Because this data type contains a mixture of doubles and characters. And then you use MPI type create struct, and this is basically the first element, which is the count, the number of blocks again. This is the block length. It's an array, 1 and 1, 1 double, 1 character. This is the displacements, 0 and 8. And these are the types. The first one is going to be double, second one is going to be character, and then you pass in sort of the type that you generated. So I marked it as old type because everywhere in the examples you saw that this 0 and 8 is mentioned as old type. Otherwise, it's a new type that we are getting. I just named it as old type. So here we have basically, we are constructing another sort of, let's say, create a struct on top of this create a struct. So we committed that type. By the way, if you are not using sort of your types in communications, probably you can get away with committing it. If you want to use it as an argument to build another type based on this type, which what we are about to do here is you can get away with this one. It's completely okay. And then here we basically did the same 2 blocks and then array of the same block size. It's going to have 3 elements, 3, 1, 2, and 3. Again, 3 here, displacement array. Again, struct works with, where is the struct? Struct works also for displacement, it also works with a byte. So we don't have any version of a struct which works with number of elements. That's good to bear in mind. So what is the type array that we have? It's old type and old type. And so this means that we are building another type based on this previous type. So now we're going to have double followed by a character and then double followed by a character because we have the two blocks basically. So that's how it looks. And then again, everything is the same. The count is 1. You send the buffer with a type of new type, and you free the resources that you have allocated. So MPI CC struct and MPI run. Whoops. You see that exactly the same messages that we have been sending over and over with different sort of type constructors. We go to the next one. Okay, this was the example. Maybe we can take a look at this one. Let's say assume type 1 has this thing, this type map. The extent is 16 for this one. Now this is our block length. The first one is going to be 2. The second one is going to have 1 element. The third one is going to have 3 elements. But these are the array of types that we have. So 2 means that associated to float, it means that the first 2 elements are going to be floats. That's why we have a float and a float here. Next element is going to be of type 1. That is a binary. It's a double followed by a character. That's why we have a double followed by a character. Then the third element or third block length is going to be 3, and then that's associated with MPI character. That is why we have a character, and a character. 3 characters. So now, why do we have these second numbers? That's the displacement array. So 0 is associated with MPI float. So that is why we start with 0. The next element is next to it. So float is 4 bytes. So 0 to 3 is going to be the first one. Starting from 4 is going to be the next float. Now that we shift to the next sort of item, it starts with our displacement starts with 16. That's why our double starts with 16. And this needs 8 bytes to get to the character. So 16 plus 8 is 24. Next one is 26 on the line. So that is why we start the character, MPI character associated to that with 26. And then each character is 1 byte. So that is why we have 26, 27, and 28. This is a very nice example to understand everything. The next one on the line is subarray data type constructor. We have an example subarray.c. We're going to see it in a second. So this one is, as the name suggests, it's a subarray. If you want to sort of pick a subarray of a whole array, you can use this one. So this dimensions, that's the number of dimensions. It's a positive integer. You can have array of sizes. That's the number of elements of old type in each dimension of the full array. And then array of subsizes, the number of elements of old type in each dimension of the subarray. And then array of starts, that's the coordinates that the subarray is starting in every dimension. And then you have something which is called an order. An order is basically how C and Fortran basically do ordering. So C usually does it with row major, and Fortran does it with column major. But it doesn't necessarily mean that if you are using C, you cannot use MPI order Fortran. So you can basically use whatever you want, depending on the application or depending on your needs. And then the next thing on the line is old type and new type. This is pretty much, we have it in every type constructor. Note that everything is in and only the new type is going to be the out. And here, the subarray type constructor creates an MPI data type describing an n-dimensional subarray of n-dimensional array. The subarray may be situated anywhere within the full array and may be of any non-zero size up to the size of the larger array, as long as it is confined within this array. It has implications in MPI IO in section 14.11. We're not going to worry about that. We're not going to deal with that right now. We're going to skip these. Before jumping into distributed, let's go to, what was it, subarray? Yes. So here we try to have a two-dimensional array, let's say. And then the size of array is going to be a 3x3 array. And then what we try to do is to take a subsection, a subarray of 2x2 from that 3x3 sort of array. And then the starting index is 1 and 1. So we're going to start from the middle of that 3x3 array, the full array. And the order, we're going to use this MPI order C. That's the row major one. And this is the call to subarray. We fill in all the information needed. This is just plug and play. And then you commit the type. You create the buffer associated to that. You try to uniquely populate the main buffer. And we are going to print some information about the size. Again, we haven't talked about those size stuff yet, but we just passed that. So this is for printing. We don't care. This is the original sort of array. We print the original array. And then after we receive we send the buffer, and then after we received it, then we print only the subarray that we have, we were interested. So let me MPI CC subarray and MPI run. So there we go. The original array is having this shape, and then if you remember, the indices were 1 and 1. So we start from here. So we are interested into this, 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 and this. And this is exactly the pattern in the subarray. So that's 1 and C, that's this element, 2 and D, this element, and 2 and D again here, and 4 and E is the last element. So this is how we picked a 2x2 array out of a 3x3 array. So that's the subarray. Now I'm going to talk about distributed array data type constructor. That is for the cases when you have, for example, a very large global array, and then you want to, for example, give sub-portions, or let's say sub-arrays of that global array to different processes. So this is a very nice one. So that is D array. D for distributed, array is for array. And then you have the size, for example, size of process group, and then you have the rank, then you have the dimensions, you have the array of G sizes. That is the number of elements of type old type in each dimension of the global array. That's for the bigger array, the largest array, let's say. Then you have array of distribs. Array of distribs is just distribution of array in each dimension. And then you have dargs. That is distribution argument in each dimension. And then you have array of p sizes. That is the size of process grid that you want to associate to that in every dimension. And then you have the order, which we already talked about it. It's going to be either C or Fortran. It's row major or column major. Then you have old type and new type. So let's take a look at darray.c. In darray.c, exactly here we have the same sort of argument list that we were talking about: dimension, size array, distribs array. Distribs array has some predefined variables or predefined values. Darg also has some default sort of or predefined values, and then the sizes. So if I want to break this down, is that the biggest or the large array we have in this case is a 16 by 16 array. That's the global array. And we want to have the processors of, let's say, this is our process grid, a 2 by 2. So if we divide 16 by 2, it's going to be 8. So for every process, we're going to have 8 by 8 sort of array or matrix. And collection of all of them is going to be corresponding to 16 by 16 matrix. So this is basically what we do. We have our new type, and then we create the D array. We pass in all the necessary arguments in there. We commit the type, and then we need to allocate the local arrays. This means that this is going to be 8 by 8. That's the size array. Number 1, which is this one, size array number 1 is going to be 16. Divided by p size array number 1, it's 2. 16 divided by 2 is going to be 8. And then for columns, the same thing. It's going to be 8 as well. And then we're going to create, I'm sorry. So now we're going to create sort of a local array. That's this structure. It's going to be a double followed by a character. Whoops. Here, we're going to use malloc, rows multiplied by columns and times the size of the struct that we have. And after we have the memory needed for storing the local array, we want to populate the local array as uniquely as possible. So in this case, we are using indices I and j to populate it. And then we're going to have now the global array for every process is going to be null, but except for process number 0, because process number 0 is going to collect all the subarrays into itself and construct the whole global array. And that is the size array. This is going to be 16. This is going to be 16 times the size of the struct, which I think it was also 16 if I'm not mistaken. Because we had a double 8 and a character which was 1, it was 9, but we have padding, so the extent was 16. So there we go. We're not going to talk about these things because we haven't talked about collective communication, but all these things are doing is basically taking process 0 is going to take all the information from other processes, and then he's trying to construct this 16 by 16 global array for us. And then finally, we free the resources because we used malloc, and we free the handles of those types that we created as well. So we say MPI CC D array, but in this one, I'm not going to use the, we have to use a 4 because that we use the grid of 2 by 2 processors. So that is why this example is a little bit different from the others, because the others we ran with 2 processes. So A that out. Okay, there we go. That's the global array. I know it, it doesn't look nice, but this is quite beautiful. Hopefully it's a 16 by 16 sort of global array. Okay, so this was the array. And by the way, this also it says that the constructor supports HBA-like. This is the high performance Fortran. And it has also implications in IO, I think, somewhere. We're going to see these things later, most probably. Okay, these things we don't care. Okay, address and size procedures. Okay, so far we have worked with relative displacements. So when we were talking about displacements or array of displacements, we were talking about relative displacements. But now we can also use absolute addresses. But you need to remember from the previous episode, for those large count versions of h-index, and construct, and I think h-index block, you cannot use absolute addresses because the type for displacements is not MPI int, but it is MPI count. So care must be taken there. So, but you can use also absolute addresses. And in that case, the displacement, we said it's always relative to the base of the buffer. But if you use the absolute address, it means that displacements are relative to address 0. That's the 0 address in your memory, in your RAM. So at that constant, MPI bottom basically shows the address 0 for you. And then, yeah, then you can count even the, with MPI get address, you can get the address. And then you can have relative displacements with MPI a int diff to get the subtraction of two addresses. You can use also MPI a int add to get the addition of those two addresses. And these two methods, these two functions are made basically to make MPI programs portable. And it is also, you should not use minuses and pluses for, let's say for address arithmetics. Better use these ones because you want to make your applications as portable as possible. That is the MPI get address we were talking about. You give the location, that's the in, and then it gives you the address. For example, you have a double called D, you give the address ampersand D, and then it gives you the address. Okay, and it gives you in this type format, MPI a int. We have an example here, absolute address. We're gonna take a look at it in a second. So then we have an advice to users. C users may be tempted to avoid the usage of MPI get address and rely on the availability on the address operator ampersand. Note, however, that ampersand cast expression is a pointer, not an address. ISO-C doesn't require that the value of a pointer or the pointer cast to int to be the absolute address of the object pointed at, although this is commonly the case. Furthermore, referencing may not have a unique definition on machines with a segmented address space. The use of MPI get address to reference C variable guarantees portability to such machines as well. So this is again an advice to users. So usage of MPI get address, MPI this int, a int diff, and a int add. These things are good for portability. Again, to ensure portability, then for arithmetic of addresses, use this add and diff. So this is add. It takes a it takes a base, and it takes a whoops. Okay. Till here, this video is gonna be again around 23 to 25 minutes. I'm gonna stop here, and then we're gonna have part 3 of data types in MPI.